Do you have any questions on the midterm exam? I saw a major issue for the last problem. Let's take a look at it really quick. First one pretty simple. It's just a hierarchical modeling method. You write down every single module's Verilog, and then assemble them together and instantiate every single thing in the top. I don't see a big problem from you guys at all. So you guys are doing this really well. And the second one, no major issues as well. Some of you didn't finish the top, but I believe if I give you enough time, you should be able to get it done. So it's not a problem at all. These ones, I can directly find the answer from the solution, right? So this is -2 n to the -2 to the n minus 1 power to the n minus 1 minus 1. Because it's if you put a 1 at the MSB, you are getting -8, right? And the largest positive number you can get is MSB has to be 0, and all the other digits has to be 1. So it's going to be like 0, 1, 1, 1, which is 7, right? Okay, and the next one, we have solution over there in the in-class. Definitely you are allowed to have multiple always. So I've seen a lot of examples. Okay. And then simple swap, just swapping 2 digits, use a concatenation, and then just do a simple swap. No problem. And number 6, only 2 of you probably made it wrong. I just the memorization stuff, right? Just IR. When RS pin is 0, it's doing the IR, right? It's sending the register, the configuration code to IR. Otherwise, it's going to be a data register. And this is floating edge. Okay, floating edge will enable it. And this one, you need to put a unit after it, right? So this is 9600 is how many bits per second. If you do a 1 over 9600, you are getting how many seconds per bit, which is exactly the data width I'm asking for. So you can directly just write down 1 over 9600, and which is giving you 0.104 milliseconds. Okay, that will be the bit width. So every bit takes about 0.104 millisecond, or 104 microsecond. Like you guys can handle all the other complicated problems, but whenever it comes down to a very simple division, I see like 50% of you guys just fail this one. So blame your elementary school math teacher or something. I don't know. 1 over 9600. You guys have a calculator. I'm seeing all different answers. A little bit puzzled. But it's not a big issue though, since a lot of you already know what that means, right? It's just simply 1 over 9600. Okay, and for the last one, so you use the compare. I think use the compare is fine, right? And the C code has S0 in front of S1, but you don't have to follow that order in your assembly, right? You could just use, so when you do compare, if you do compare S0, S1, it's doing a S0 subtract S1, then you're stuck. So if you use compare S0, S1, what kind of flag you could use? So it's if S0 is larger than S1, right? Then do something. Else S1 equals S1 plus 1. Is that the case? So if you do compare S0, S1. And this is basically running S0 minus S1. So if S0 is larger than S1, and your C is what? Your C is 0, right? There's no carry out because S0, if S0 is larger than S1, if you do a compare, your C is, so C is 1. If this one is getting satisfied, C is 1. C is 0, no carry out. What about S0 equals S1? Hmm? Did it say anything about it? Let's take a look real quick. So that's a problem, right? That's a problem. I don't think whenever they are equal, it's doing something to C. It only tells you when it's larger than that, it's C is 0. When it's smaller than that, C is 1. So let's take a look. Where's compare? Ah, it's on the top. Okay, it's a bad day. So when they're equal, it's not doing anything to C, right? So if you are using S0 in front of S1 for the compare instruction, right, like this, and you have to look at Z and C at the same time, I think. Because when they are equal, it's not doing anything to C. It's probably C just remains the same. So it's not being overwritten. So the previous C, which was calculated or impacted by other code in front of it, dominates. So this one is not doing anything to C. Right? Unless you tried it and let me know what the difference is. But actually, now I don't see anything whenever it's larger than or less than. It's dealing with C, but when they're equal, it's not doing anything to C. So for this case, if it's larger than that, can you use C here? Will C work? Because they're going to jump, right? It's going to be NC or C, right? Let's see if we do C. It won't work because this is larger, so C is 0, right? If it's non-C, we're saying, hey, C is 0, we want to jump. But this also covers when they are equal. It's not having any impact to C as well. But if you swap it, what could you do?
Jump C.
Yeah, jump C to. Yep, that works. Then you have done. Do something. Or done, right? Whatever. I'll just write down this one here.
Wouldn't you do jump C done if it was S0, S1?
If S0 is what?
If you have compare and then S0, S1, wouldn't you do jump C done? And then jump to done?
Hmm?
That would jump to done, right?
Yeah, so this is where you're using C, right? Yeah. and else is actually should be done. We're not assuming anything, right? Should be do nothing. Do nothing, not do something. Do something will be a problem. So if it's done, and for other cases, you're gonna skip this one and do adding S1 1, because this instruction is directly adding 1 to S1 and assign it back to S1, and then go to the next one, which is nothing, right? Just finish. Wouldn't have any impact to anything. You see the difference here, right? Because this is gonna give you a definitive answer, so you can use jump C. If you do S0, S1, then you don't know which one to use. Jump C or jump NC wouldn't work, right? Would it work at all? Should we try it? If we do like adding Z to it, that's too many conditions. Unnecessary, right? Because this is very simple. All right, so this is the last one. And any other questions on any other problems? No? We'll keep going to the SPI modules. SPI. Which is the SPI module. Okay, so the SPI digital block is a communication protocol or port. It's a synchronized communication port because both modules are being synchronized by one clock, which is called SCK. And that clock is being generated by the leader. Always, okay? So you can see the leader SPI and follower SPI. And usually the leader SPI is a device with a CPU in it, right? Like a microcontroller, the IPGAs. But you can also modify our IPGA as a follower, because the IPGA could be a very complicated SoC, system on chip, or could be a very simple digital block. And the follower is usually just a sensor. Only one individual SPI block is probably just designed or being put into that sensor module, right? So it's usually a follower. And again, see there are four pins. One is the chip select. SS is active low usually, and SCK is a clock, and both SCK and chip select are generated by the leader. Okay, both SCK and chip select. Sometimes it's called SC, sometimes it's called SS, or sorry, CS or SS, CS or SS. Oh, I didn't look into that. So what SS? So the second one is a select. What the first S means, I didn't really pay attention to it. But usually it's using a CS. So when it's showing a CS, it's a chip select. That's what I usually see. But SS, I don't know. I forgot. And but it doesn't matter. It's just a select pin. Just making a selection. It's active low. Okay. And then you have MOSI and missile. These are two data transmission lines, and you can send data and receive data at the same time. And so that's a benefit of using SPI. And also at the same time, it's both devices are being synchronized by one clock. Okay, if you just think about UART, so what UART looks like. So there's one, another one, TX, RX, RX, TX. Okay, and there isn't a common clock to synchronize both devices, which means even though you are trying to synchronize it, your rising edges to falling edges could have time delays. So you won't be able to synchronize both transmission and receiving. So where's the clock for UART? Where's the clock? So there's no clock for transmission and receiving, right? Is there just a clock internally sending data one by one, and they have agreement on the baud rate? So I'm pulling this up and down at a certain baud rate, and the receiver knows it, then just keeps taking data into the vectors, right? Using the index to keep increasing the index to put it into the vector. The same for the other direction as well. So it's slightly different. And SPI is usually running at a higher speed compared to UART and I2C. So I2C is a little bit different. It could be important to know, especially for interview questions. So I2C is another very popular port. It has SCL and SCL is a clock, right? And there's a SDO. Is it SDO? SDA, yeah, that's right. SDA. So it's a data, serial data, and serial clock. It doesn't matter which direction, it's bidirectional for just one line, right? Just one line. So a lot of times it's also called a one-liner communication port. It's taking a lot less number of pin resources compared to the SPI port, right? But the thing is, this is one slower than the SPI. So SPI is usually running at several megahertz, but I2C is usually like 40K or something, or maybe 400K. So it's a lot slower. So given that, which one is better for a relatively longer distance communication? I2C or SPI? Which one? For long distance transmission. SPI is faster, a lot faster. So long distance means what? More parasitic capacitors, right? Because all the cables, they have caps along it. So in that case, you have more caps to charge and discharge, which means it's going to slow the system down. So in that case, if you run SPI for long distance, it's going to cause problems. It's not able to drive it efficiently to charge and discharge all the caps along the cable. So SPI is usually, the longest is several meters. But usually we don't run longer than a couple meters for SPI. Usually it's just on the PCB. It's actually just tens of centimeters actually. But I2C could go very, very long. So because hot springs, the hot tubs, wireless network is a temperature wireless network we built for a senior SUM a couple years ago. So it's a one-liner temperature sensor that we used, and let me draw the layout for you guys. So it's the application in the real world. The property is pretty big. Hot springs have been there, the hot springs over there. So I have hot tubs, 24, 25 hot tubs, all different ones. Okay, and they want to keep the natural scene on the property instead of having a lot of construction. So they keep all the hot tubs as its natural scene, right? So it didn't change too much to it. So the thing is, we have to use a light pulse, which has AC 110 AC to power up our temperature sensing system. So they have been using their staff members to probe the temperature and change the temperature on the sign just next to every single pool manually. So the thing is, we need to have a wireless temperature sensor to probe the temperature everywhere for it just for the hot tops and send it to a little data center on the property. So the thing is, the distance between the light pole and the hot top is usually like 10 meters at least. Okay, so we need a solution for this project, right? Would you guys propose some solutions to it? So first, what type of temperature sensor should we use? So there are multiple options. Thermocouples. Have you used thermocouples in M&I? Thermocouples is what? It's just like two metal pieces attaching to each other, and whenever there's a temperature difference, it's gonna reflect the temperature difference to the two terminals of the metal wires, and there will be a very small voltage change, right? Thermocouples is like a little metal here, and you have two wires. And are seeing an analog voltage change according to temperature changes. Is this a good option for this application? How would you design it if you are a designer?
Probably waterproof.
Yeah, waterproof. The thing is, you have to drill a hole to the hot top here, right? And then have a thermocouple here. And what's next? Thermocouple.
Micro controller.
No, actually.
Or analog to digital ADC.
You have to amplify it first, because you're not expecting couple voltages changes across the thermocouples. Otherwise, it becomes a power generator, right? It's only millivolts level, and all these analog changes has to be amplified, right? And the amplifier will amplify it to a certain range. You'll probably need multiple stages, and then that range of analog signal will be fed into an ADC and got a digital data out, right? And then can use your MCU to log it. So the problem is, where do you place every single component in the system on the property? If you are using a thermocouple, when would you like to amplify and digitize the analog signal? Where?
Pretty close.
Pretty close to the pool. So you're expecting a very bulky PCB to do all the amplification and the digitization just right next to the pool. And the problem, you probably don't have the space to do it. You're only drilling a little hole, right, to the pool, and then you don't want to place a big box of PCB. Doesn't have to be big, but it has to be a box to host the PCB over there, right? So you need a PCB just next to the pool, every single pool, for amplification, digitization, and MSU, and microcontroller. It'll be quite a space, quite a footprint on the PCB. So this is probably not a good option, right? What else? So this is bad. So what about, hey, I don't just put amplifier and ADC close to it. I just have a little thermocouple sensor. It's a little tiny piece, and I drill a hole and place the sensor into that hole, and it's just able to have a contact with the water. And then I use a wire. I just use a wire, and 10 meters of wire to the light pole, and then I have a little box attached to the light pole, do all the amplification and digitization, and then MCU, so I can send it to the wireless center somewhere else over here. What about that option?
Probably lose a lot of accuracy.
Yeah, because these are millivolts level, and you are having a 10-meter transmission line for millivolts. That's crazy. All the noises, even probably someone step onto the concrete, and that kind of vibration will get into the wires and will give you like 10 millivolts changes. And your signal is only like a couple millivolts. So that's not good. So never do long distance analog signal transmission. Okay, you should digitize it as soon as possible. Okay? So this is not a good option because you have to customize everything and made a PCB out of it. And there are other sensor modules which are being built in a little tiny chip. Okay, so that chip is basically a temperature sensor. It is able to sense an analog sensor, digital analog temperature data, and then directly amplify and digitize it. So the sensor's output, so it looks like this actually. And there's a cable. And here's a probe. And this is about 1 inch. And this is waterproof. It's been wrapped by a rubber material. It has a little chip inside. I couldn't see, but it's all sealed. Okay, and the signal here is directly digital already. And you are looking for, so this sensor has different digital outputs and have different options. This looks like the same shape. So it seems like they're designed for water temperature probing, probably. Okay. I still have like 50 of them in my lab. So there are different options: I2C, SPI, or UART for that digital cable here. So definitely you want to pick up higher speed or longer distance. Longer distance. You don't need a high speed, right? The temperature is not changing at 5 megahertz. And you don't care, right? You only probe it or probably update the data every, let's say, couple minutes actually. So even I2C is overkill. So definitely I2C will be the good option. You want to look for a temperature sensor which is able to convert the analog temperature data into digital signal, and you want to pick up I2C for long distance, right? So it's a slow data transmission, but long distance. And so we do have, so at the swimming pool we have as I2C temperature sensor. We have a probe being put in here with the cable, and the cable definitely can reach out to. For these cables usually don't run very long, but for the Ethernet cable, it's called Cat6, I think. Have you heard about that? Cat6. It's just Ethernet internet cables. They can go really long. You can see the Ethernet cables within the lab. They are running through the whole building. It's probably over 100 meters, and it's rated for 50 to 100 meters. And I actually tested. I put an I2C sensor over here and probing the temperature data, and because this cable from the manufacturer is not very long, they don't know you are using it for that long distance, right? So this is probably only a foot or something. And then right after the cable, you strip it, and then you connect it to a Cat6 Ethernet cable. And for some reason, that cable is designed for long distance. It's probably lower parasitic capacitance. And then you buy some of the Ethernet connectors, and you use a certain tool to make the connection to the from the connector to the cable at the other end of the cable, right? And so you can just plug in that terminal into your PCB's female connector, and eventually receive the digital signal from this guy. So that one can run for at least 100 meters. I tested, which is amazing. So for temperature sensor data, if you have to run it through the wire, you have to use a Cat6 internet cable. So another question is why you are not directly sending a wireless signal over here instead of using a cable? Why not just directly shoot it out using RF?
Because it's a lot of components.
You still need a lot of components like a microcontroller. You need an ESP32 with a Wi-Fi PCB board on it. So and you also need the power. Where does the power come from? Where can I get the power from? Just next to the pool? It's not available, right? But for the light poles, you have 110 AC, and you could directly convert it to a DC, and then step it down to 5 volts to power up everything over here. Okay, so that cable has data transmission, also has power and ground. So the sensor's power and ground is being shorted to your data center or your microcontroller PCB board. You only need one PCB for this one, for this guy. Okay. So it's going to be one PCB for one pool. Okay. So one cable connect to one PCB, and that PCB will send the signal out wirelessly to a data center, and that data center communicates with the internet, and it can eventually see the data from the website. Let me see if I can still find it somewhere. I think it's this guy. So still up running, but I think it was part of last year. These are names of the hot tubs from the property, and
minus 200 degrees Fahrenheit.
yeah, it was not plugged in. It's not plugged in. So that's the code of the wireless communication from the ESP32. So we used it for the robotics 2 class as well, for streaming real-time video data from the car for face recognition. It's a really powerful module anyway. So this is application for the SPI modules. It's not good for SPI, but good for I2C. All right. Cool. And let's look at the in-class where we're at right now. Okay, so the first one, you know the answer. The second one, what is the frequency? So we do have 100 megahertz frequency available on the board, right? And we need to divide it into a certain frequency for our SPI. So it will be only slower than that, because that's the fastest signal or clock available on the board, 100 megahertz. So if I'm counting up to 25, see here, see this code, Verilog here? It's counting up to 25, and then I flip it. I toggle the clock pin, ICK. Every time I count to 25, I toggle it. Every time 25, I toggle it. So which means for the ICK, which is a clock for SPI, right? You need to define the ICK, especially for the leader. It's 25 counts, 25 counts. So how many counts per period? $50. Okay? And you have 100 mega counts per second, which is the original clock. What is the resulted frequency by doing this number of counts? So what you are doing is it counts up to 25 and then toggle it. And the counts is actually using the 100 megahertz clock, right? How would you calculate it? This many counts per second, and this many counts per period, and we're trying to get the frequency of the resulted of the divided clock. How do we calculate it? Yeah, 100 mega counts per second divided by 50 counts per period. So this resulted in 2 mega period per second, which is frequency. This is actually hertz, right? So this will give you a 2 megahertz. All right. So in the future, we'll do a very quick quiz about this. If I'm giving you a certain desired SPI clock frequency, I would like you to find me a count for it. Okay, should be pretty simple.
Code, would it count from 0 to 25?
Hmm?
So would
Yeah,
that
it's
be
just
26 or still 25? 26.
should be 24, right?
26.
So it wouldn't be. Wait, no, I mean 0 to 24 will be 25 counts, right?
Oh, yeah.
So that's why the textbook use 24 sometimes. But just one clock is probably 0, 1, 2. Yeah, I think 24, 25 will be very similar. To make it super accurate, probably 24 will be better. Yeah. And I think because 2 megahertz compared to 100 megahertz is 50 times slower, it probably doesn't really, it's not obvious changes, right? But for one count difference. Yeah, I think 24 is a better practice, I think. It's good. And for the naming problems, right? So the naming of the SPI, all the society starts not using MOSI missile anymore. So the textbook uses PICO and POSI. That's how you pronounce it. So PICO means peripheral in, controller out. Okay, and CS is chip select, SCK is serial clock. But majority of the you can see, even though it uses PICO and POSI, but they call it leader SPI and follower SPI. But you still need to know the names, because just in case of the interviews they ask you the questions, right? And you can see that MOSI are connected to MOSI, and missile are connected to missile. You can see the newer version of the chips are gradually making changes to it. Because this is relatively old technology, and all these products available on the market were all developed like 10-15 years ago at least. So these are being mass produced, like billions of chips every year. So you can still see a lot of the old names from the data sheet. But you as engineers just need to know what's really happening here, okay? So you are bulletproof, for interviews and any other things. We are looking at data sheets, you know what are they. And the clock signal, in which module the clock signal should be defined. And for the clock signal and the chip select signal, they are both defined by the leader, just like you guys know. So that's how we designed it. We designed it that way, okay? So compared to the microcontroller assignments, there's no way that you can modify it, because it's always being sent out by the microcontroller, and you couldn't really change the clock because it's always from the microcontroller. But for this one, you are the designer. You can do whatever you want, okay? But the only thing is have to be compatible with the peripherals. Right? The peripherals are having SPI modules, then your leader or your receiver, your follower has to match it. You can see the first example over here, given by the textbook, right? We have the SPI leader transmitter and the SPI follower receiver, okay? So leader transmitter is what? Leader transmitter as a pin is what? MOSI, okay? It's MOSI. And for follower receiver, it's also MOSI, right? It's also MOSI. So leader transmitter and the follower receiver, it's just one line. It's one line. That's why it's it's two modules in two different blocks. But we are talking about the same data line. Okay? So because the leader is transmitting data, so over here we can see the leader has to define the clock. I'm going to give you guys a couple seconds to take a look at it. And for all the declarations of the registers and everything, you can just ignore it. By looking at the Verilog, I just pay attention to the key parts. It's actually really simple, right? It's very, very simple. just take a look at it. The first half of it. So what did you notice over here? What did you notice? Could you let me know what did you notice? Just by looking at it really quick. So first you have two always blocks. The first always block is rising edge. It probably doesn't matter that much. It's just the rising edge of the clock to create a SEK. So the first always block over here creates SEK, right? It's counting up to 25. You could put 24 over there, but it's actually toggling the SEK every time when it counts up to 25. So it's creating a 2 megahertz SEK clock. And that's it. And the second always block is looking at the negative edge of the SEK. Okay, so the SEK is already created by the first always block. It's already available, and the SEK and the second always block is looking at the negative edge of that SEK, of the created SEK clock, and start doing something, right? Because the communication started with the transmitter. If the transmitter is not doing anything, the receiver is not going to receive anything. So the transmitter started the event. Okay? So you can see where it gets started. That's the important thing to look at. So if sent, we're not seeing any sent signal over here in the sub module, so it must be from the top. So in the future, when we design the top, we need to give a send signal to it to start it. So that's the first state, and it doesn't do anything except start creating an initialize the index, right? And then moving to the start state, the first thing to be done is pull down the SS signal, which is the chip select. And that chip select, remember, is active low. So the leader is actually pulling it down to make a chip select to enable the transmission. So after this is put down, the transmission will be enabled. And at the same time, I'm going to draw on the paper. So I think this is related to problem number 8. So take a look at this. Well, so this is when this is being put down. So at which edge of the SEK? This is my question. You have SEK, right? SEK. See here, negative edge of SEK is doing this. However, when it enters this state, it will never look at this one anymore. Okay? I don't care what happened before. I only care about whenever it's getting enabled. Alright, so SEK is the negative edge of the SEK, and SS will be enabled. At the same time or not? At the same time with the falling edge of the SEK or not? Everything here happens at the same time because this is a non-blocking assignment, and this is being updated by the negative edge of the SEK. So this is on the sensitivity list, right? So whenever negative edge of the SEK arrives, this is going to happen whenever it's at this state. So you're expecting what here for SS? What you're expecting here? It's being put down at the same time. It's just a time delay here. It's being put down at the same time. Whenever it assigns a 0 to it, it's a falling edge. So which means before it's ready, whenever the transmission is done, you need to put it up to disable it. Okay, so it was 1. Now I put it down to make it 0 over here. What about MOSI? The data. data becomes available. See? It's non-blocking. So it's like all the 4 lines, boom, same time. From right to left, same time. Okay? Make sense? So data becomes available. And you want to draw it this way. So before, it was nothing, just high impedance. So as this edge, data becomes available. That's it. And after that, at every falling edge, we'll make a new data available over here. The positive edge of it doesn't really matter because it's not on the sensitive list. So the positive edge of it is not really doing anything for this guy, right? However, for the follower, so you see, it's placing a data to the data line over here, and then moving the index is pumping every single data from the vector to the data line. And for the next one, the transmit one, it's not really doing anything. It's just looking at the indexes, if the index is 0 or not. If the index is already reaching 0, then it assigns a very lost index to it, and then you're done. So it's not actually doing anything. So that's a major part of the code of the leader transmitter part. So you need to know that this is important because every time you're looking at the SPI's operating mode, you want to pay attention to SS and the data assignment when they are being placed on the data line. So for this one, they are being placed in the same state. So this happens at the same time. Okay, and for the next one, these are so the leader and follower, they share the same lines, SDK, SS, and MOSI, right? It's the same line. If this one is being put down, up and down, these will be sensed by the follower as well because that's the same. They share the same wires. So for the follower, I mean, even though it has a lot of lines of data code, we don't care about it. We just look at the important part. Okay, so the first one, hi. So this is a positive edge of the SDK. But the SDK, they share the same SDK. So it's not doing anything at the negative edge of the SDK. So my question is, does that make sense? Do we really want to do something at the negative edge for the follower receiver? No, because it's enable it and only place the data onto the MOSI, the data line. It's not stable yet. Here it's not stable yet. If the follower, because this is the follower receiver, is receiving data, right? The transmitter is sending the data. You want to sample the data in the middle. So SDK will keep moving. So that's a clock. No one can stop it. Clock's a clock, right? No one can really stop it. But for the chip select, you can enable it, disable it, but clock is always running. Okay? And now you look at it. When the follower receiver takes in the data to its vector. Rising edge. Okay? So it's rising edge, but also SS has to be activated, which is not SS, which is 0, right? So when SS is 0, which means it has to be a rising edge of the SDK. At the same time, SS has to be 0. It has to be enabled. The chip select has to be enabled. It's a active low. Okay, so what's happening over here is the rising edge, the follower receiver will sample the data. It's exactly in the middle of the data. Why? Because the next falling edge will place a new data to MOSI. By what? By the leader. This is always activated. Take a pause and let me know if this makes sense. Why your leader transmitter is gonna send a new data at the falling edge next? Why not here? That's how you design it. It's negative edge clock. Okay? So every time the index is being updated, so the last time, the first falling edge will send a 1, right? We'll send the 1 data here. It's the 1 data, which is not 1, not 0, it's just something, right? We don't know. Could be 1, could be 0. And whenever the negative edge, the next negative edge of the SDK arrives, you got to update the index, so it's gonna update your data at the MOSI line. It's gonna update it. Okay, so it's gonna keep following that pattern. Okay, keep following that pattern. So it's always placing the data to the MOSI, to the data line at the falling edge of the SDK, and the follower receiver will take in the data at the rising edge of the SDK. And SS has to be 0 at the same time. So it's taking it in. See, MOSI being assigned to the vector with a certain index, right? And then immediately it's being decremented by 1. So next time will be a different location, but will still be whatever available on the MOSI data line, which was updated by the negative edge of the leader transmitter. And this will change next time, and then the updated one will be placed to your vector over here. And this one will get a new data for you. Does that make sense? So the key point is, first, your data and your chip select, it becomes available at the same time because of this guy. Because this little piece in your Verilog, and after being synthesized and implemented to the FPGA, your SS and MOSI will be available at the same time. Like this. For the first data point. And your negative edge of the SDK will update your data on the MOSI line. It's just one of the operating modes, right? So by looking at this timing diagram, and then let's go back to the operating modes over here. So SPI could operate at different modes, and these are the 4 combinations of the modes, and I'll let you tell me based on the example given by the textbook, right? Which mode is this being operated at? So polarity of the clock, it's CPOL, it's the polarity of the clock. It's a parameter to be set up. It's not a parameter we're setting up in your Verilog. You didn't see this parameter. It's just 4 modes that could be possible or available on the market. For example, the microcontrollers, Arduinos, right? Arduinos. And there will be a register to control the operating modes for the SPI. But our example from the tutorial or from the textbook is only one of the 4 modes. It's not all of them. And we cannot change it unless you change the code, right? So it only works for one of the modes. And this is a snapshot from the textbook. This is a little typo here. So it shouldn't be CHPA. It's a CPHA. It's a phase. PHA, the phase. PHA, it doesn't have SE over there. It shouldn't be CHPA. It's a CPHA. Okay, just let you know. And so for the code we just talked about, right? It didn't show a floating edge over here, but it should have a floating edge. Over here is an extra floating edge over here, and that floating edge is synchronized with the chip select floating edge over here. So they are being synchronized. So whenever negative edge of the clock arrives, you got a negative edge of the so it's getting started, right? Chip select is being put down. See? Boom. Boom. Okay? Do you notice that? Two floating edges at the same time. Because in the Verilog, remember, it's the negative edge of the SEK will trigger this to be put down. You are giving a 0 to SS. So that will be the same thing over here. It's a floating edge here. You didn't draw it, but I'm drawing this for you guys for here, adding it. It's a floating edge, and we'll have a SS, which is this guy is being put down, right, at the same time. So definitely the polarity of the clock of the SEK is 0. Okay? What about the phase? The phase. We're looking at what? We're looking at MOSI, right? MOSI. Okay? So for MOSI, data was made available instead of sampling the data by looking at this guy, right? So at the floating edge, data was updated. So which means it should be the beginning of the data over here instead of in the middle being sampled, right? So we are looking at this guy. See, the floating edge and your MOSI have the first data available. So the mode designed by from the textbook is actually running at 0, 0, right? So CPO to CPHA is actually the mode 0, 0. Does that make sense? Okay. Now let's go to the next one. Any questions on this? Can you change the mode over here for the Verilog? You could, right? You could. So for the microcontrollers, there will be a certain register you can write into. It's a 2 bits, right? You can control the 4 combinations of the operating mode SPI by changing the code in that register. And for the next one, also 2 blocks. Okay, these 2 scripts. Now it becomes the leader receiver and forward transmitter. Okay, leader receiver and forward transmitter. And now we are talking about missile. And it becomes the leader receiver. Sounds interesting, right? So the leader is actually receiving the data, which makes sense because the forward could be a sensor, and the sensor can have a SPI digital block in it, right? And it makes sense that the sensor is sensing the data and transmitting this out to the receiver, which is the leader, which is the microcontroller, so you can register it into your memories, right? So that's what's happening over here, and that's actually the sensor module I just gave to you. Did you see that sensor module? Okay, everyone should have a sensor module. It's a light sensor, and that has a SPI module in it. So the light sensor is a photodiode. It has a, I put it on the table. I didn't, or I didn't. I'll do that for you. So take a look at the pinout over there. What you have, CS. Okay, CS is the chip select. It's active low. And you have a not connect, so don't have to connect anything to it. And SDO is the data out. Data out, right? It's the missile, okay? It's the missile. And SEK is the clock. So clock is generated by what? By your FPGA. and have a VCC and ground. So this is a 3.3 volts device. So only use it with your IPGA. Don't try it with the microcontroller. It's gonna possibly damage it if you use a 5 volts to power it up. But for data communication wise, it should be fine because it's sending out, not receiving it. So 3.3 volts logic being sent out from the sensor is still being recognized as a 5 volts, as a 1 for microcontrollers, right? So higher than 2.5 volts. So your SPI leader receiver and SPI forward transmitter modules are provided over here. The same concept. Now let's take a look at the code real quick and just notice, pay attention to the important parts, right? Even though it's pretty long, but we only look at the important parts. And what are they? Clock, right? Who is a positive clock? So positive edge of the clock, which is 100 megahertz, is being divided into a 2 megahertz clock. And even though your leader is a receiver, but still a leader, right? So leader should always define clocks. So even though you see a SCK on the light sensor module, it wouldn't output any clock. It's not generating a clock. So it has to be the IPGA to generate the clock. And that's, here it comes, like this, right? So that's how that works. And chip select, the same thing. So the leader has to initiate that process. So it's a positive edge of the clock. If we start drawing it as we did for the last one, so we have SCK, okay, SCK. So it's a positive edge of the SCK. Clock is always running. You can just keep drawing it. So the positive edge of the SCK does what? What does it do? Yep. Okay, it's always available until it's done, right? Assuming we need at least 8 bits for it. What else? Here. Did it place the data or receive the data over there? So because this is the leader receiver, my question is it receiving the data within this state or this clock cycle? Because definitely the leader is not supposed to place the data to missile, right? It's a receiver, it's not a sender, it's not a transmitter. So it's only receive something, right? But is it receiving anything? Nope. Nothing is being received. It has to change the state, and whenever the next rising edge arrives, it takes in that missile data on the line and put it into the vector. So which means it only takes in the middle. So we still have to look at the when the data is being sent out, right? The missile is being sampled, should be in the middle. So expecting this, right? This. But now the question is when the data is getting started, right? When the data is getting started. So it has to always sample in the middle. And where it's getting started, we should look at the transmitter over here. All right. So the transmitter is a full-load transmitter. It's not generating the clock, but however, it's able to see the clock because they share the same clock line. So it's able to see it. So whenever this is being put down, okay, so whenever the negative edge of the clock, and it has to be 0, right? It has to be 0. Shouldn't be at the edge. Has to be 0. So it's going to be this negative edge. With the first positive edge of the clock, pull this down, right? Put this down. So it has to wait for the floating edge of the clock, and exactly the SS will be 0, which is great. And then, see, whenever this is 0, whenever this is negative edge, it directly places the data onto the missile line. So it's available. So how would you like to draw it? It's going to be the starting point of the data, right? This is high Z, nothing. So data starts from here. And every time at the floating edge, the data is being updated. Same to this guy. Okay? And this is how this missile module works. And by looking at the mode chart above, so let's take a look at it. Which mode is this being operated at?
CPLL1, CHCA1.
Yep, it's going to be a 1-1. Is that the case? Right? So see SCK is rising edge. So you are here, I didn't draw it, but there should be a rising edge. The rising edge pulls this down, okay? And the floating edge start the data. So start from here. So it's basically C polarity, the clock is 1, and also the phase is 1. So it's a 1-1 mode for this operation. Okay, and for the SPI modules, it doesn't have to be a byte. Okay, you could define the length of the data. If you look at it here, right, totally customizable. Because if you look at the transmitter, I put an 8 for data length, and you can put a 12, you can put a 9. Doesn't really matter, because always, depending on the length of it, right? It's just subtracting 1 to the index every time, and just directly placing every single bit to a certain vector from for the receiver. So you can totally customize the length of the data for SPI. And the receiver and transmitter are being synchronized by the ICK. So I2C has an address line. If you think about I2C, take a look at this one. So I2C peripherals. So for I2C data transmission, you hook up the ICO and ICA to the same data bus, so same bus, and you can have multiple sensors. If all the sensors are communicating with I2C protocol, you could connect multiple I2C sensors to it. So the thing is, because they share the same data line, it's the same ICA, right? So every single device, they have to have a certain address in order to know like which one should start taking in that data available at the SDA data line, right? So that's how that works, because every device has a address, and the I2C protocol knows that the first byte to be sent is actually the address, so it's going to activate one of the I2C peripherals and then start communicating with that certain one. So for the SPI modules, but looking at the Verilog, do you see an address of this device? Do you see address of it? There's no address. It doesn't, like we have a certain if this one has an address for the receiver side, it should be whenever that register have that value received, which is the address, which is the byte. Then I start doing something, but it doesn't have an address. It's directly taking in the data no matter what. So the problem is, are we allowed to have multiple peripherals connected to the same MOSI missile lines? How could we handle that? Let me repeat my question again, okay? For I2C, how many lines for I2C? How many lines? One clock, one data, right? Two. So is clock carrying any information? No. It's just boom, 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 right? What about ICA? Yeah, ICA is the only line carries information. If I want to send out the address to identify a I2C, because all the I2C peripherals are connected to the same clock and the same ICA. If I make a 1 available on the ICA, every single peripheral is going to see that 1. Same as zeros. Right? Because that's the same data line being shared by all these I2C sensors or peripherals. So the only way to communicate to one of the peripherals of the I2C on the I2C bus is to have every single I2C have an address. So that address is built in. It's being written into the Verilog by the digital designers. It's built in to that I2C device. So your so the leader device has to send a byte, which is the address first, to the ICA line one by one, and all the I2C devices are receiving that address bit by bit, and eventually all the whole byte is being received and compared with its built-in address. If it matches, it starts receiving data after that first address byte. Otherwise, it wouldn't do anything. It won't be activated. That's how I2C works. So I2C has the first byte, the protocol of the communication. The first byte is address byte. All right, that's I2C communication. However, for SPI, did you see address matching protocol over here? No, there's no address. It's just whatever data is available on the MOSI line, it's start taking it in. So in that case, how could we connect several or more than one SPI peripherals to the same data bus? It's very practical, right? It's a very practical problem. Because in the real world, you could have just one microcontroller controls like 10 sensors at the same time. But you only have one SPI module on your microcontroller. You're not expecting like 10 SPI modules on the microcontroller. It's going to take up so many pin resources, right? There's only like sometimes one, sometimes two SPI modules. So basically for one microcontroller, you only have, for example, one SPI module, then there will be only one MOSI, one missile, one SDK, and one SS. That's it. But you need a 20 sensors being hooked up to one brain. How? Whenever you are sending data to MOSI, every single sensor is responding. They are feeling everything is being treated the same way. Hey, you are sending data, let me receive it. Every single one is doing the same thing. How would you be able to make a difference?
Could you make different chip selects for each one?
That's right. But how?
Like a finite state machine?
It has to be a combinational logic. I want to hear one name of that combinational logic. A decoder. Right? Your microcontroller will send, if you have like 20 peripherals, how many bits of the decoder of the code do you need? Would you need? 5. 4 will give you 16, right? So 5 will give you 32 combinations, can definitely handle 20 devices. So for that one, then you have 20 different combinations of the code, and then we'll send it to a decoder to enable each CS pin individually, right? If you want to send the data to one, then you activate that one only by sending a decoder code first to control the CS. So how that works? On the hardware. Same clock, same MOSI, same missile. How that works? How would you design it? Is that decoder or encoder? We'll think about it. One chip select the pin.
It would be an encoder if you're sending.
So you definitely need some GPLs, right? Couldn't be just one pin because there's only one pin, couldn't control it. Right? So probably this one shouldn't be used. So 3 pins, for example, 3 GPLs will give you 8 combinations, right? That case, so 3 combinations. So everything connect to the CS of each one. You have more here, for example. Will that work? I'm still thinking. I don't know. I haven't designed this before, but just let's think about it. Brainstorm on this really quick. Depending on how you design the decoder, right? If you have a 0, 0, 0, for example, you want to select this one only, so you are giving a 0, 1, 1, 1, 0, right? So how to design the decoder? That could be the very good quiz question. How would you design the decoder? Input, output, right? Easy. A, B, C, input, output, Y1, Y2, Y3, Y4. Right? 0, 0, 0, you give a 1, 1, 1, 0, and keep going. 0, 0, 1, you do a 1, 1, 0, 1. Okay? Just keep going. So how many peripherals you can control by 3 bits? 8. And then we are looking at the little decoder circuit here. You could, but by just looking at every single column, and then looking at all the ones available over here, and then form the mini terms, right? Min terms of the ABCs, right? You can design the combination logic to control it.
Would the next one be 1, 1, 0 or 1, 0, 1, 1 or 1, 1, 0, 0? Like, would you need multiple sensors or just one at a time?
Depending on applications, but actually not. Every time you can only activate one,
Okay.
right? Because every time you are only communicating with one. 2 at the same time doesn't make sense. 2 SPIs, it could, right? If you do need to do it at the same time. No, it doesn't, because they should be different data, right? If it's the same data, why do you need 2? Right? So you need multiple sensors. It definitely they are sensing different data, and then your missile line will be different. So yeah, every time only activate one, so it has to be the 0, shifting the 0 bit by bit, and eventually design the decoder over here. Right? It could be a combination logic, or if this is a microcontroller, you could you could write a C code to output these patterns by GPLs. Cool. So that question is answered. Have we answered all the questions over here? Yeah, number 8 is answered. Number 9 answered. 10 answered. 11 and 12 will be on Thursday. Okay? Alright, let's see you during the lab. Not ready yet. Oh.
I was just bringing up this question. I used the S1 in this place using the C to jump to the end.
Because this is S1 subtract S0, right?
Which-
And if so this is larger than that, so there won't be any C. It's gonna run this guy.
Isn't it similar to the in class today? Like if S0 is greater than S1, then we get carry in.